This electro-optic modulator works because an applied electric field alters light propagation speed. The clever bit here is changing refractive index electronically. Laser light enters a non-linear crystal, such as lithium niobate, as an ordered optical carrier wave operating at extremely high optical frequencies. Applied electric fields exert direct electrostatic forces that distort constituent crystal molecules, directly shifting the material's local refractive index. This molecular distortion forces incoming light waves to travel measurably slower as they propagate through the solid ferroelectric crystal matrix. By dynamically varying the local electric field strength, engineers directly control the precise optical phase of laser light exiting the crystal. This fundamental mechanism enables ultra-fast optical switching, with modulation bandwidths extending comfortably into the gigahertz frequency range. However, simply delaying or altering the phase of a continuous laser beam presents an immediate engineering hurdle, because phase shifts do not change raw light intensity or overall beam brightness. If a photodetector at the receiver end only measures light power, pure phase changes pass through completely undetected without generating a readable electrical data signal. Applying a basic electric field merely shifts wave crests in time, leaving the light amplitude constant and making binary switching impossible with a simple isolated crystal. Liquid crystal devices function as electro-optic phase modulators when used without polarizers, but they similarly lack built-in intensity switching without additional optical configuration. Without an integrated optical arrangement to convert phase into power variations, electro-optic phase modulation fails to produce usable intensity signals for standard receivers. To resolve this limitation, engineers convert phase shifts into measurable amplitude or polarization changes using specialized optical arrangements and polarization filters. By routing the light through polarizers or interfering split optical parts, subtle phase delays convert directly into distinct light intensity variations at the receiver. In ferroelectric crystals like barium titanate, controlling polarization states alongside phase allows robust intensity modulation suitable for optical data networks. Because the Pockels effect dictates a linear relationship between potential and refractive index, phase modulation responds smoothly and predictably to applied electrical signals. This linear response ensures that complex electronic data waveforms translate directly into clean, undistorted optical modulation without introducing chaotic harmonic distortion. The bigger problem was that driving a complete optical phase shift requires extraordinarily high electrical potentials across the modulator crystal. The specific potential required to induce a phase change of chi radians is known as the half-wave voltage, denoted as V pi.
For standard Pockels cell configurations, achieving this half-wave phase shift typically demands hundreds or even thousands of volts across the active material. Switching thousands of volts within nanosecond timescales to match gigahertz signal bandwidths appeared completely impossible using conventional microelectronic driver components. Standard solid-state electronics cannot toggle such extreme voltages at gigahertz frequencies without destroying transistors, generating immense heat, or causing extreme signal attenuation. To solve this high-voltage challenge, engineers construct a parallel plate capacitor geometry directly across the electro-optic crystal matrix. Placing parallel capacitor plates across lithium niobate or barium titanate establishes a uniform static or low-frequency electric field within the crystal volume. Because the electric field inside a parallel plate capacitor depends linearly on potential, precise control over electric field magnitude is maintained. In nonlinear ferroelectric materials, where the Pockels effect dominates, the material's refractive index changes in direct linear proportion to this internal electric field. The phase of laser light exiting the crystal depends directly on the exact length of time required for light to travel through the material. Higher field strengths increase refractive index, slowing light velocity and extending transit time, which directly shifts the exiting optical phase in proportion to voltage. To handle the demanding half-wave voltage requirements, high-voltage amplifier circuits are designed specifically to switch several hundred volts within a few nanoseconds. These specialized electronic circuits allow electro-optic modulators to serve as ultra-fast optical switches, rapidly gating laser beams for high-speed digital communications. Beyond inorganic ferroelectrics, modern electro-optic modulators also utilize electro-optic polymers and organic materials, featuring strong nonlinear optical coefficients. Applying a low-frequency or DC electric field exerts precise subatomic forces that distort the shape, orientation, and spatial arrangement of constituent molecules. These molecular distortions generate two primary phenomena: a controllable change in light absorption and a simultaneous shift in refractive index. Engineers leverage these combined electro-optic phenomena to impose controlled signal modulation across light phase, frequency, amplitude, or polarization state. By optimizing crystal aspect ratios and narrowing electrode gaps, the effective half-wave voltage is minimized while preserving high optical transmission efficiency. In laser-controlled modulators, microwave transmission line electrodes guide electrical signals alongside optical waveguides to maintain phase velocity matching. When electrical signals match the speed of propagating optical carrier waves, cumulative phase modulation builds efficiently along the entire length of the crystal. This synchronized velocity matching enables clean modulation bandwidths extending far into the gigahertz spectrum while operating at manageable drive voltages. As a result, delicate high-speed electronic data streams map seamlessly onto laser beams without physical moving parts or mechanical degradation. By coupling electrical potential directly to crystal refractive index through the Pockels effect, electro-optic modulators bridge high-speed electronics and optical physics. Overcoming the barrier of high half-wave voltages with tailored capacitor electrodes and fast switching circuits unlocks gigahertz optical modulation capabilities. Whether modifying phase, frequency, amplitude, or polarization, these solid-state devices convert low-frequency voltage signals into high-speed laser optical carriers. This seamless translation of electronic signals into pure optical phase shifts makes the electro-optic modulator an indispensable pillar of modern photonic technology.